So for I took a limit of my rate, and that was just the natural evidence basically. And I was like, this is
email on my Twitter and just
and it's the only place I've actually changed my it's the only place I've changed it because everything else
Oh, why is that still on the screen? Right, docs. So I've got all this set up at home. Stupid. Right, that's better. Right, so the trick is to force Teams to use a different bandwidth channel, and it uses higher bandwidth on that. So that's what we're doing. Right, okay. It looks like we're pathetically going. Let's have a look. Right, okay, so recursion. Right, the first thing that you'll get asked, which is the hardest thing in the whole world, is what is recursion? So has anybody got, in this context of programming, what they think is a snappy, and there isn't one, a snappy definition for recursion? Go on, Harriet.
I've got a function that calls a version of itself with different parameters.
Right, so we've got a function. It doesn't have to be a function, it can be subroutine, but yeah, so a function that calls itself. What was the last bit? Right, that's the key. Otherwise, it would be what we call infinite recursion with different parameters. Right, okay. Anyone got another thing to add to that? I'm going to say not different parameters, but different parameter values. So it's the values, not the parameters. Right, Hugh. Anything to add? So that's Harriet's definition. A definition for recursion. This is what you were doing on Monday, remember? But does that explain it? It's funny, in dictionaries, the definition for recursion is often, stupidly, because it's amusing, is see recursion. That's the definition, which doesn't help you at all. Yeah, go on, Dan. It is a form of decomposition. It's also sometimes called the fourth type of something. Yeah. Not everyone calls it that, but that is somehow it's classified, because it is an iterative process. But that begs the question, what are the other three? Right, so what are the other three forms of iteration? So that's for, while, and then repeat. So yeah, it is a form of iteration. It's a strange form of iteration. Right, so we've got, it's a function that calls itself with different values. That's key. A form of decomposition, well, yeah, it is, because it's modular. It's the fourth type of iteration. Anything else? I can't see the chat, so if anyone's saying anything in the chat, I wish I had another monitor. That's why I have 3 monitors at home. So I've got 2 work monitors and then the second one, an extra one. Right, how do we spot recursion when we look at an algorithm? No, that would just mean a function. There are two things that all recursive subroutines have. We've identified one, but there's another one that's crucial. This computer's struggling to do OBS and this at the same time. Right, so one of the features, Harriet said, it makes a call of itself. So it calls itself within the body of the function. What's the other thing? Yeah, Rob.
Is it like, once it's broken down and solved all like small solutions, like to combine them to get a final solution?
It sort of depends exactly what it's doing. Sometimes there is like a combination type thing where it's like winds back. But it depends what it's doing. I'll show you a nice one in a sec. When you were researching this, did you see like factorial? Done as, yeah. I don't know why. It's the world's worst example. Because yeah, it does demonstrate functional recursion, but no one would ever in their right mind calculate a factorial using recursion. You can just do it with iteration, really simply. No, there is one thing that you'll see. So you've got the recursion, so the thing that calls itself, there has to be another element. And that's what we call a stop condition, well done. A stop condition. There has to be something where there is a choice. Do I recurse or do I stop doing that stuff now? So there has to be a stop condition. One of the things that recursion makes use of, it uses a stack. But it's automatic. The stack is used to keep track of values just through the process of function calling. What I've always thought about recursion is that it's ridiculously hard to clearly explain, but actually when you see recursion, it doesn't make much sense, but you can see how good it is. It's really strange. You'll see that in a sec. Right, okay, so that's some like basic things, but another way of thinking of when something is naturally recursive, we do these sort of things as humans all the time. Right, a naturally recursive process, something that is going to be suitable for recursion, is something where an initial problem can be broken down, okay? Right, so where an initial problem, so that's the decomposition bit, but there's a real key caveat on this. Right, so when we break this down, the thing that can be like an alarm bell to you to say, oh, actually, this looks quite recursive, is when you break that problem down and you end up with a simpler problem, or closer to the answer you want, but it looks like the original problem. But in a simpler form. Okay, so, right, okay, so let's just look at the stupid factorial. Okay, so we'll look at that, and then we'll look at something a bit more practical, one of the cool algorithms. And it will be introducing a data structure that we haven't formally looked at, but it's a good place to start. Right, so let's just have a look at factorial, just as an exercise in this process of looks like the simple problem, looks like the original problem, but is actually closer to the answer. Right, so with factorial, 4 factorial is what? How would we calculate 4 factorial? 4 by 3 by 2, and then technically by 1, but it doesn't make any difference, does it, at the end? Right, there is another way of working that. How else can we write 4 times 3 times 2 times 1? Right, now this is that decomposition. So let's simplify this problem. So we say, right, well actually the problem is, I don't know how to calculate factorial, but I know that 4 factorial is 4 times 3 factorial, although I don't know how to calculate 3 factorial. So I'm just going to write it like that. So actually, I've got, oh, it's just 4 multiplied by something. However the hell you calculate 3 factorial. But I can write, I don't know how to do 3 factorial, but I can write 3 factorial as 3 times 2 factorial. And again, I don't know how to calculate 2 factorial. So what I can do is I can say, well actually, that's the same as writing 2 times 1 factorial. What is 1 factorial? 1. Oh, don't have to work anything out. The answer's 1. So that actually is 1. So what we're looking at as a problem, we're saying actually this complicated thing of working out what 4 factorial is no more than saying it's 1. The only thing we've got to work out is 1, and then it's just a multiplication of a number. That's why we end up with this solution. So we might create a function called fact. So we'll just say func fact, and we just have one parameter. We'll call it n, because everyone calls it n for some reason. And we know if we get a value of n equals 1, that the answer is 1. So all we need to do, and this is how you tend to start your factorial, your recursive problems, you just say, right, okay, what's the stop condition? So I'm going to say, right, if n equals 1, is there anything else that gives us 1 for factorial? 0. Yeah. So if I say, right, okay, let's just say we could do it like this if we wanted. Say, if it's, should put double equals. If it's a 1 or a 0, we're going to say, right, you know what, the answer is 1. So it's a nonsense thing. You wouldn't ever use this to calculate a factorial unless you were working on a stack machine. Then you would, but in general we wouldn't. But we say, right, okay, if that's not the case, then this is what we need to implement. So you can see this is our stop condition. So let's just identify that in the working out we've done. That was our stop condition. That bit. The rest of the code that we need to implement has got to do this bit. So this is the work. So I have got to formulate that. It's a bit like doing functions in maths, this. All right, a little bit like that, which a lot of people don't like, functions in maths. Proper functional programming. So we need to, this needs to be the body. This is what we've got to write in code. So if we were given n equals 4, what we're going to say is, right, okay, so it's not that first case, so we're going to do an else. So whenever you're looking at a problem that you've been given, so let's say you get given a recursive bit of code, you're looking for an if. And you're looking for an if, you can see here there is no recursion happening. That must be the stop condition. So that is our stop element. Right, so now I'm going to say, right, well actually, the answer to the if n is 4 is 4. So I'm just going to return that answer. So I'm going to literally write return. And I'm going to say, right, well, it's not 4, it's n, isn't it? Because that's what I'm using as an example. So I'm going to say n times, and then I'm going to call the function. Because that's what my little working out says. It says, actually, it's n times 3 factorial. But 3 factorial is n minus 1. So I'm going to say, and this is what comes back to what you said, Harriet, about the parameters change. There has to be something, and I'll talk about that in a minute. So I'm going to say, right, well, yeah, looking at this, we're saying it's n times, 1 less than n. So I just say, right, well, work that out then. I've got a function that works out factorial, even though I haven't finished writing it. But I know I've got a function that does it. And that's it. Often, recursive solutions are simple because it's nearly like something that we don't do anymore, not on A-level computer science anyway. It's nearly like declarative programming. You're concentrating solely on formulating the logic of what you're doing. You're not worrying about complicated constructs and things. We just got an if. We make a decision, return that as the answer, or say, return this as the answer. So I'm implementing the working out, the worked example, literally. Okay? And that is it. Now, so you can see this is the bit that you're looking for. So when you're given a bit of code and they say, tell me something about this code, always look for this element. This is the recursive part. So that's the point at which we recurse. Right, and there is a very, very important relationship between the stop condition and the recursive line. You want, and you can check this when you're looking at stuff, you want the manipulation of the parameter to move you towards your stop condition. So with this one, it needs to be counting down somehow, because we're looking to trap 1 and 0. When would this factorial algorithm, and this is the algorithm that everybody quotes, when would this fall apart? Yeah. There is in this, there is no definition for a negative. Okay. We could build something in to do something about it and reject it. So you could, I don't know, you could like do an extra if and say if it's negative return 0, so it's undefined, or throw an error is what you'd probably do, or something like that. Okay, so that is an example. It's not a practical example. So let's have a look at something where we get this facility where I've said initial problem can be broken down, looks like the original problem but simpler. So let's have a look at something really important, something that is like a cornerstone of computer science. Oh, let me draw that. Right. Can anybody tell me what this... I've got to think now, hang on. I can't think and draw at the same time. What this structure is called in computer science. Can anyone tell me the correct term? We traverse these things, yeah. Make that easy for myself. Pascal's triangle? No. But that's like saying this piece of cheese that I've got out of the fridge that's mouldering looks like Pascal's triangle. Which, you know, I wouldn't say that. Oh, I've cocked that up. I'm just gonna undo that bit. Yeah, right, that'll do me. Right, you're saying that's a tree. Right, someone also said it's a binary tree. Why are you calling it a binary tree? What do you mean, give me one of two things? Right, that is the vaguest vague of vagueness. You are the king of vagueness. Right. Why is this called a binary tree? Two branches. Right, when do we have non-binary trees? Give me an example. Give me an example where we would have a structure to hold non-binary trees. Well, yeah. Right, your classic example of a non-binary tree structure would be a hierarchy. Organisation chart, folder structures, they are non-binary hierarchy. Can you imagine if when you were organising your, and you lot are hopeless anyway, but can you imagine if when you was organising your folders on your C drive that you could only have two folders inside each other? God, it would be deep. So yeah, we have a hierarchy. Hierarchies generally can have multiple items at a layer. These will only ever have two, because they're binary. Right, that's what this is, but there is a base data structure that a tree is an example of. Anyone know what that is? Super important. Right, what's the more mathematical name for a network? Network's correct, but we wouldn't ever use that as a technical term. A network is another example of this thing. No one know? A graph. Oh, did he? You said that's not right. Well, you're a loser then, aren't you? Right, the graph. It is a base structure, a mathematical structure that can represent all the other data structures. An array can be represented using a graph. It's a linear graph. Okay? A tree is a form of graph. We'll get on to graphs properly, but I just wanted to introduce that. Right. When we're looking at trees, the only thing we ever know about a tree is this thing. Yes, Hugh. Have you?
Yeah.
Why? I think, well, they sent out letters, didn't they? But then they changed the times anyway. Yeah, I mean, I'm recording it, Hugh, so. All right. Right. A tree. Trees are interesting because they are indeterminate in size. We don't know anything about them. They're a little bit like linked lists. Okay, linked lists. What do we know about a linked list? What's the only information we know about a linked list? Yeah, where it starts. In a tree, we only know where the starting point, and this is the interesting thing about a tree, it has a definite start, which we call the root. Which is why in folder structures, we call the C drive the root. In fact, they even use the keyword in Linux or Unix. I hope it's some use. Right. Let's have a look at some technical terms and then we'll come back to the recursion for this. So the root is the starting point. It's the only thing that you have any idea about with a tree. What are the items that are in the tree called? These things.
Nodes.
Yeah, these are nodes. So this first one is called the root node. What are the stick things called? Particularly in tree. What was that? Branches. Yeah. What's the difference between the branches that go this way and the branches that go that way? What do you think we call them? Left and right. So that's a left branch. That is a right branch. In general, binary trees are used to store ordered data, whatever that data is. So I've done an alphabetical thing here. Right, okay, so we've got node, a root node. We've got a general term node, which is where we store our data and our links, our branches. What do you think we call the ones at the end of the tree? End? Leaf. Leaf node. So you can identify a leaf node because it has no branches. There must have been people really like belly laughing when they came up with the names for all these things. It's like the nibble thing. It's like someone must have like spat out their coffee if they were drinking coffee when they came up with it. Or left a cyanide sloppy apple on the side when they came up with it. Like someone was wont to do, unfortunately. Right, okay, so this structure can store things alphabetically. One of the things that we do with trees has been taken away from the A-level specification, and that's to do with the language translation, so compiling code. One of the acts of the compiler is to build an expression tree and a parse tree, which contains the entire structure of your program in a tree organization, and then we can like process that tree. But we don't do any of that anymore, weirdly. It was really good stuff as well. But a process that we do a lot with trees is we walk trees. So you may have heard of tree walking, if you're mad. Right, we have got to get used to two processes. Tree walking is a form of search. And it's an exhaustive search. So walking is visiting every node. But we don't call it walking, we use a fancier name. What's that? What? Anyone know? It begins with T. Traverse. It's the sort of thing an American would say. We'd say we're going for a walk, and they would say, I'm off to traverse to the shops, or whatever. You know, like instead of saying something's a tap, they call it a faucet, don't they? But they have to use the correct technical term. There you go. They don't spell anything right, but there you go. So we call tree walking traversal. Okay, so it's called traversing. So we when we're looking at algorithms for doing search, we've got two types. We have a pure search, which is locate the item. I will share this whiteboard, so it's like try and get down some of the nuance of what I'm saying. So locate an item in a structure, or we have a traversal, which is to visit. And it's really, really important when you get questions that you look at it carefully and you make sure you're either doing a search or a traversal, because they're going to be different. A search will stop when you find something. A traversal doesn't stop until it's exhausted the graph, whether that's a tree, a linked list, or whatever. So that's... why does it do that? Right, okay. So one of the classic things that we do is we traverse trees. Now what I'm going to show you is, if you get this in a question, I'm going to show you the manual way of doing it. And you're going to look at this and you're going to look at me and you're going to do what? Right, so I'm going to just draw another tree. I'm going to put numbers in it because it's easy for my brain to work with. Although I've not helped myself there. You've got to be comfortable with trees, so you've got to be like a tree hugger, if you want to think of it like that. Right, so we'll have that tree. So here's my root. So what we're going to do is we're going to do this, and this is a bit of a mouthful. We are going to perform post-order traversal of this tree. We're going to do it physically, and then I'm going to show you the recursive algorithm for it. Right, so because it's a traversal, what they'll expect is you to write down the order that you visited all the nodes. All right, so always from a traversal, you will always be expected, and there's different sorts of traversals and things that we do, but you'll always be expected to produce the output. What's going to be visited. And the order matters, because the order shows that you follow the traversal properly. Right, but doing this physically is actually quite, well, it is quite magic. The first thing we do is we're going to put a marker on all our nodes. There are three forms of traversal that we could do. The three forms are pre-order, in-order, and post-order. Okay? Post-order is really important to us because when we've got expression trees, so when we're converting from what we write as an expression when we're coding, so if we like put a times b minus c divided by x, that's no good. The computer can't process that. So we push that into an expression tree, and then we can process the expression tree using post-order traversal, and we can get something that we can turn into machine code or evaluate using a stack. So this traversal is really, really critical to compilation. Right. So I'm just going to write this down in the top left. You'll see there's a little bit of just sense to this. So I'm going to draw an empty node each time. Right, so for post-order traversal, we start with a mark in the center of the node, and we go through. Oh, stop trying to make text. We draw a line cutting the node to the right after it. Post node. If we were to do pre-order, which they shouldn't ask you in the exam, but they could, we would do a line going this. Now, don't worry about why we're doing this line. You'll see the magic in a minute. Where do you think in order goes? In the middle, but it goes down. Don't go up. That's the only one you've got to be careful of. I don't actually know what would happen if it went up. We could do it as an experiment. Right, so in general, we're going to get asked to do post-order traversal. So what we're going to do is a starting point is we're going to take a pen and we're going to do lines that go outside of the node from the center. Do them reasonably long because that's going to matter in a minute. So just mark each of the nodes with a post-order line. So I'm going to do that first. So we end up with quite a bizarre diagram. Okay, so that's step one. The next is even weirder. We're going to draw, and I don't know whether you've ever done this before, where you're scribbling and you're doodling and you like draw a line round some stuff on a page. You like envelop it. So what we're going to do is we're going to take a pen, we're going to start above the root node. So I'm going to start here. I'm going to put a fat line on this actually. Let's go fat line. Right, and I am going to draw around this tree, sticking to the contours of the tree, and whenever I pass one of these weird lines I've just made, I'm going to write down the node. So just watch me do it first before you do it. Oh. Don't unselect it. Right. So I'm going to start there and I'm going to go, and the key is that you go counterclockwise. So I am following the contour of the tree closely, which is why we do the lines first, and then I hit this line. So what I'm going to now do is I'm going to keep it in blue because it's going to be a nightmare changing pen. I'm just going to write down, 4 was in that node. Going to carry on my line, and I'm going to go around. Oops, I've gone a bit wrong. I now hit the 12. Carry on. Get to the 10. Be really careful when you're writing things like this, because obviously, is that the number for 12 and 10, or is it 412? So, in an ideal world, put some delimiter in there. Don't use space as a delimiter. It's not a very good delimiter. Keep going. Get 14. Keep going. Now, what you will notice with post-order traversal is you visit the root node last. So I'm keeping on going. I'm going round and round and round. Get 79. Keep going. Keep going. Get 78. Keep going. Get 85. Yeah. Keep going, and eventually we catch the 76 and we finish. Right, so that is the tree traversal process, and that is the manual way of working it out. So if in an exam you get given a tree and they say perform a post-order traversal, this is what they're going to expect you to do. All right, because it's the sensible way of doing it. Now, like I say, this is a little bit meaningless because there's no context to what we're doing. So these numbers don't mean anything. It's just the order that post-order traversal has given them to us. Just to show you, so you can do this, let me do an in-order traversal. So I'm going to use a different colour. Well, I'm not, because this don't have many colours, this. I'll do it in blue. In order cuts in the bottom, so I'm just going to do my cuts. Oh, that is stupid. Now I can't select it. Oh. Right, let's just... How ridiculous is that? No, it doesn't work on this. Right, okay, I've got a floating 6 now. Brilliant, thanks for that. Right, I'm going to put this... Right, I'm going to have to cut it in red so I can see it. Right, so I'm cutting down the middle, the in order one. Right, I'm going to do the traversal again. I've already drawn the line, so I'm just going to follow it round this time. So I'm going to use red. So I'm going to go round whenever I cut. So I get me 4. So that was the same as before. But look what happens. So I then get 10. Keep going. So it's when I'm cutting the in order ones that I'm worried about. Keep going. Right, catch the root this time. Keep going around. 78. 79. 80. 85, and that's it. Right, so what the in-order traversal has given me is the numerical order from the tree. So that has given me the numerical order. So that was in order, yeah. If what? Yeah, but that would change the structure of the tree, wouldn't it? I'd have to traverse it again.
Like the 12 turned to a 15, wouldn't it?
I'd have to delete the 12 first. Yeah, no, trees are interesting. You can't just like edit trees. You have to remove nodes and add new nodes. I'll show you that in a sec. Right, so the post order doesn't make much sense, but that's the one that will always be asked to do in the exam. The in order you can see. No, it's not. No, it's not. Right. We'll come back to the recursion in a sec. I just want to it's not by chance. Right. Let's start with an empty tree. So we're going to build a tree up, a numerical tree. Right. What would the root node be pointing to if we've got an empty tree? Nothing. Now, how do we say nothing when we're coding? Null. So initially, the tree is empty, null pointer. Okay, just like with the linked list, we point to nothing. Right, so give me a number then, Ralph. Let me bother to write. Right, okay, right. So this is the process of building a tree. So we create a node, put the 2 in it. So we'd have a node class and we can have a go at building that on Friday. Right, and then we say, oh, we've got a tree. Excellent. We'll point the root to it. Right, give me a number, Harriet. Any number. 15. Can you see how hard it is? When I do all these numbers on the board all the time and you're like going, oh, look at him, little lamer. Lamer, he can't even think of a number. It's not easy. Right, we start, and we have to process the tree now. So I want to put 15. So I started the root node, and I go, oh, there's something in there, let's have a look. We look at 2. Now it's sort of the opposite of binary search, this, building a tree. We say, right, okay, there's something there, so I need to follow a branch. I need to create a branch. But is 15 bigger or littler than 2? Bigger. So I'm going to create a right branch. And I'm going to put 15 there. Grace, give me another number. 18. Right, okay. So we start at the root. We say, right, okay, there's something there. 18 is bigger. There's a right branch. Let's follow the right branch. We get to 15. And we say, right, okay, 15 is bigger than that. There isn't anything, because this was a leaf node. So let's put a number in. Harvey, next number.
22.
Why are we going bigger each time? You are lame. I'm going to do it. I'm going to do it. But blimey, come on. You are pretty. It's like Pavlov's dog. It's like count with Pavlov. Right, okay, what did you say? 22. Harvey, was it 22?
Yeah, 22.
Right, again, we'll start. It's all right because this highlights something horrible about trees. We start with 22. We go to the root. We can see 2's there, and we say, oh, it's bigger than that. Oh, follow the right branch. Get to 15. We go, oh, 22's bigger than that. Follow the right branch. We get to an 18. We go, it's bigger than that. Nothing gets displaced in this tree. Right, Emily, give me a number. Don't go bigger than... No! Stop programming yourself. You don't listen to them, just give me a number. 12, thank you. Right, so we're going for 12. We start at the root, and we say, okay, like 12, it's bigger than 2, so let's follow the right branch. So we're down to 15, and we go, right, okay, 12, less than 15. So we need to go left of the 15. So there's nothing there, so we put a branch in and write 12. Jacob, one more number. 18. No, you can't have 18, we've already got it. No. We would be storing key values.
What about negative?
You can have a negative number if you want.
Oh, okay,
-4. Right, okay. We start at the root. Ralph! We start at the root. We say, right, -4. Oh, that's less than 2, isn't it? Right, there is no left branch, so we're going to create one, and we're going to put -4. Right, I'm going to leave it at that. Right, if we'd have kept going with Pavlov, and he's counting, you know Pavlov's dog, where you, condition people?
Oh, you mean a bell thing?
Yes.
Yeah. Oh.
It's like social conditioning, yeah.
Rang a bell every time his dog's 8, so whenever he rang a bell, he spoke to himself.
Yeah.
Yeah, and then he stopped. So he just rang his bell. Did it without...
Yeah, whatever. Right, so, if we'd have kept going down the old Pavlov counting system, can you see what sort of shaped tree we would have got? A straight line. Essentially a linear representation of a bunch of numbers. But what we actually use the tree for is to organise ordered data. It uses linked lists, but it uses 2 linked lists when we implement trees. Now what that gives us the benefit of is the nice quick insertion and deletion that we get from linked lists, but also the benefit of binary search, where we discard half the information each time. If a tree is linear, we call that an unbalanced tree. It's the worst type of tree, because it means when you start searching it, you're doing a linear search. So you've gone to all that effort, and you've ended up with a linear search. There are some awesome algorithms to do with tree folding and tree balancing. They're awesome, I love them. It used to be on the A-level. You used to have to be able to do them in the exam. Write an algorithm to fold a tree. really cool stuff. But you do it all recursively, it's really good. Okay, so we've got this structure. Now, back to this is all because of Ralph. Because I like you to give me valid questions. It might seem like crazy, but you said it was luck. So but Ralph's really like chuckling inside because he thinks it's all going to go horribly wrong in a minute. Right, so I'm going to do an in-order traversal. So I'm going to start off and I'm going to do my little markers from the centres down. Then I'm going to trace an outline anti-clockwise around this tree. So I'm going to start at the top of the route and I'm going to work anti-clockwise. And every time I meet a node, I'm going to write its contents down. And unfortunately for Ralph, it's actually just going to coincidentally work again. Because life's just full of coincidences, isn't it? There's no order. It's all just pure chaos out there. And look at that. Magically, it just sort of worked again. So, yeah, in order, they don't ask us for that. They ask us for the post. But I will, on Friday, I will show you some of the stuff where we can take an expression and we can generate a tree and then we can generate an evaluation expression in postfix or reverse Polish, which is what it's used for. Okay, so this process does work, okay? And it is a completely valid, nice bit of magic. It's a magic trick you could do to someone to show them how awesome computer science is if you really wanted to. Right, let's have a look at the algorithm for this though. The recursive algorithm for post-order traversal. Because that's what we were talking about. Let's move on a little bit. Right, okay, let's before I show the algorithm, let's just look at a tree. Let's go to my bigger tree. Right, if I started my route, I always start on my route. So the route points to a tree structure with these left and right branches. If I take, let's say I'm at the route and I decide to follow the left branch. So let me just highlight the left branch. It's a bit difficult to highlight on this because it's got so much stuff all over it. But this is the left branch, this portion. Can everyone see that? Everyone happy that that is the left branch of the tree? If I was to just point at that node, what does that tree look like? It looks like a tree. Now, I said ages ago, it seemed like ages ago, let's scroll back up to it, a problem that's suitable for recursion is something that when we break it down, it's simpler, but looks like the original problem. So, traversing a tree actually is a problem where we get a subtree. But that's a tree. So it's the same problem again, but the tree's smaller. All right, so it's a bit like what Harriet said with, we change the parameters. So actually the parameter, it's still pointing at a tree, but it's starting at a smaller tree. And we go smaller and smaller and smaller. Okay, so what that then enables us to do is to produce very little actual code. So I'm just going to write this out. So this is going to be a traversal, so it's just going to output each element of the tree. So I'm just going to do it as a subroutine. Doesn't need to be, it's not going to return anything. So I'm just going to call this post, and it's going to take I'm actually going to put a data type just so it's clear. It's going to take a node value. Right, the traversal will end if we have got a null. We are not pointing at a node. That's going to be the stop condition. So we're going to put that in first. So we're going to say if n equals null, then we're just going to stop. All right, so I'm going to write this, and I'm going to rewrite this, because I'm just thinking logically, and then I'll say, okay. Right, so I don't want to do anything. So, okay. So I'm going to refactor this in a minute. I'm just raw thinking what the logic is that I'm trying to say. So I'm going to stop if I have no node to process. If I have a node to process, what actually happens when we do post-order traversal is you might be able to see this. So let's go back to this one. We sort of start at the root and then we travel left. Okay? And we keep travelling left until we can travel no further. Then we try and travel right. And if we can't travel right, we output the node. So that's how we got the 4. So we got all the way down here. We got to there, we went, oh, can't go left, let's try going right. Oh, can't go right. So let's output the node. We've then finished and we do something called backtracking. So we go back up the tree. This is what the traversal does for us. We get to the 10. So from the 10, we travelled left. We don't process the 10 yet. We go, oh, we can go right. So we go right. And we get to the 12 and we go, oh, there's no left, I can't go left. So we're always trying to go left. And then we're always trying to go right. If we can't do either of those, we go, oh, output the node. So I can't go right, so I output the 12. And that's why I got the 12. Then I say, right, I'm done now, so I better go back. So I'll backtrack again. So I've explored the left and the right of the 10. I can't do any more. Output the node. That's why we get the 10. Then we go back up, so we backtrack again. So this is what this algorithm I'm about to write has got to do all this magic. You'll be amazed when you see how big it is. But we get up to the 14. We try and go right, but we can't go right. There is no right branch. So we output the node. That's why we get the 14. Then we go back up to the 76. So we backtracked again. Callum, pay attention, matey, because when I give you a test on this, you better ace it. Because you obviously don't need to pay attention. It's all been recorded for posterity. I can show it to your parents. Right, 76. So we followed the left branch, but we now can follow a right branch. So we go down that right branch. We get to 80. We're trying to go left all the time. So we go, hey, we can go left. So we go left. We get to 78. We go, oh, try and go left. Can't. But I want to now go right. I can. So I follow the 79 down. Try and go left. Can't go left. Try and go right. Can't go right. Oh, better output the node. So you can see that's why the 79 pops out after the 14. We're done with that, so we backtrack to 78. Oh, we've already gone right. So we tried left, we've done right. Better output the 78. We then backtrack again. But when we get to 80, we go, haha, I can go right. So I try and go right. Get to the 85, and I immediately say, yay, try and go left. Oh, I can't. Right, okay, try and go right. Oh, I can't. Okay, output the node. So that's why I got the 85. Then we backtrack. We've just gone right, so the only thing left to do is output the node. We then backtrack. We've been right. Nothing left to do. Output the 76. So our algorithm's got to do all that. Sound really complicated. Let's go down to the algorithm. Right, so I am going to rewrite this because I'm just like throwing my brain out. So I'm saying if I've got a node, I want to follow left. So I can do that by saying post order traverse the left part of this tree. So I'm going to say that. And I use dot notation like we do when we're doing the object-oriented stuff. So I'd say follow the left branch. If that left branch is empty because we're at a leaf node, that stop condition will catch it. Right, so we're going to try and go left. But we also want to try and go right after that. So straight after that, logically, we're going to say, right, when you've done the left branch, do the right branch. If you've done the right branch, we said output the node. So I'm just going to say print node dot data, I'm going to call it. So the data that we're storing at the node, we generically just call it data. There may be 5 or 6 pieces of data at the node. That's the algorithm. But it's not written very well, because I've got this. I've got a condition that I've picked up, but I don't want to actually do anything. So how can I rewrite this algorithm to make it make more sense? It's a standard thing we have to do a lot. When we look at the raw logic, but it doesn't translate directly into code. How can I flip this so that I can just do it with 4 lines of code? Look at what the if's saying. It's saying, if it's equal to null, do nothing, else do all that other stuff. How can I rewrite that condition? Yeah. I'm saying that if it isn't null, I can process it, can't I? So actually, what I can do instead of this, which is actually where this whiteboard, no, why is it? That is weird. Oh, it's there now. It does that sometimes. Right, so instead of having this bit, we can delete it. We can grab this bit and move it up. If I could actually see, let's make that so fine. Oh, it's stopped working again. I'll just rub that out then. Try that again. No, didn't want to select it a second ago. Right, so I'm going to change my logic to this. So I'm going to say, if n is not equal to null, then I've got a node to process. Otherwise, do anything, nothing. That code will now output and visit every single node in a tree. No matter how big that tree is, there's nothing there. And this is the pure benefit of recursive solutions. Often simple. Sometimes they're the only way to actually solve certain problems. If you've got hierarchical data structures, they follow the logic. But they're not fast. They're not fast because they're making multiple calls. All right. Every time you call a function or a subroutine, there's a cost. You've got to put things on the stack, return addresses, parameters. You're using stack space. But actually, you can do this iteratively, but it's a little bit more fiddly and complicated. Okay? What we get as a benefit, you get automatic backtracking. So as you end a subroutine, you fall back to the previous call. So you get automatic backtracking with recursion. So anything where you're going to try and navigate down a structure, but you need to go back as well, recursion also is. And there's a lot of search algorithms that use this sort of backtracking mentality. Okay? In fact, you can generate lots of bits of data. You can generate mazes by using what we call recursive backtrackers, which have very little code in them. And they can generate mazes of any size that are solvable. Very clever stuff. Prims is an example of it. You might do that in maths if you do decision. Do they do decision stuff?
Algorithm. Yeah, you do it with maths.
Yeah. Right, okay, I'm going to end that there if I can find my how to stop recording controls, because I turned them all off. Right, on Friday, what I'm going to do is we're going to implement this and we're going to watch it running in the debugger. Okay? Because I want to introduce you to the debugging facilities a little bit more. Controls, is it?
So, in order for